Hello students, today I am going to discuss infrared spectroscopy. This is another form of spectroscopy which is based on infrared region of electromagnetic spectrum. The light rays have longer wavelength. Since they have the longer wavelength, they have less energy as compared to the visible light. As discussed in UV visible spectroscopy causes transition of electrons from the lower energy orbital to the higher energy orbital. But in case of infrared spectroscopy, the energy needed to excite the bond is it does not has that much of energy to cause electronic transition. So here the molecules vibrate with greater amplitude, uh, and the bond will only interact with the electromagnetic infrared radiation, however, if it is polar. So the presence of separate areas of partial positive and negative charge in the molecules allows the electric field component of the electromagnetic wave to excite the vibrational energy of the molecule, and the change in the vibrational energy produces a corresponding change in the dipole moment of the molecule. The intensity of absorption, it depends upon the polarity of the bond. Symmetrical non-polar bonds in, for example, in nitrogen and oxygen, they do not absorb radiation, and so they cannot interact with the electric field. So the basic requirement for infrared spectroscopy is that the molecule under study should be polar. The main use of this technique is in determining the functional groups present in the molecule, and the spectroscopy measures the vibration of these atoms, which is helpful in determining the functional groups. The wavelength ranges from 2500 to 16,000 nanometers. Now the photon energy associated with this part of infrared are not large enough to excite the electrons, as I have discussed before, so they only induce vibrational excitation of the covalently bonded atoms or groups. Now these covalent bonds in the molecule, they are not rigid sticks or rods such as found in molecular model kits, but they are more like stiff springs that can be stretched and bent. We have springs which can be stretched and bent. Now the molecule composed of n atoms has 3n degree of freedom, 6 of which are translational and rotations of molecule itself. So 3n minus 6 degree of vibrational freedom. Vibration modes can be named as stretching, bending, scissoring, rocking, or twisting. This figure shows the different types of molecular vibration that are seen. Stretching or bonding vibrations, they alter the bond length. So, and whereas in case of bending, they alter the bond angles, while the bond length remains unchanged. So they can be divided into in-plane and out-plane modes, and they can be like twisting, wagging, and rocking. So here you can see in the figures that in-plane, we have in-plane stretching, we have out of plane, this is like twist, this is wagging, this is in-plane, again stretches, this is rocking motion, this is anti-symmetric. Okay, so these are the different types of molecular vibration that are observed in different type of molecules depending upon the functional group. Now, infrared spectroscopy can be obtained for samples in all phases. It can be a solid, liquid, or gas. In case of liquids, these are usually observed as thin films which are sandwiched between the polished salt plates like NaCl plates. If the solvent used to dissolve solid, then the care should be taken that they are not observing in those spectral region in which my sample is observing. So otherwise there will be interference in the peaks. Perchlorinated solvents such as carbon tetrachloride, chloroform, tetrachloroethane, they are commonly used. Alternatively, solids can be incorporated in thin caviar discs prepared under high pressure or mixed with little non-volatile liquids and ground to a paste to form a spear between these salt plates, and then they are observed in spectrophotometer. This is an diagram of an IR spectrophotometer. We have an IR source. We have two beams. One is passed to the reference and another to the sample. The function of these two are similar as discussed in UV spectroscopy. We have a chopper that once passes the beam of the reference to the detector, and in second turn it passes the beam from the sample. And this is how the monochromator, with the help of a monochromator and grating, they are finally trapped by the detector. The source in case of IR spectrophotometer can be an infrared light emitting radiation throughout the whole frequency range of the instrument. An inert solid is electrically heated to a temperature of around 1500 to 2000 and this heated material emits IR radiation. It can be nurse glower. It is a cylinder of rare earth oxides. Platinum wires are sealed to the ends and a current is passed through the cylinder, and it can reach a temperature of around 2200 K. In case of global source, this is silicon carbide rod, which is electrically heated to around 1500 K, and the spectral output is comparable to nurse glower, except in case of short wavelength, where its output becomes large. We can use incandescent wire source also, as which is actually a wound coil of nichrome wire, which is electrically heated to around 1100, and it produces a low intensity of radiation than the above mentioned nurse glower and blower. The light from these sources is split into two beams. One is allowed to pass to the sample, another to the reference beam. The function of such a double beam photo operation is to measure the difference in the intensity of the two beams, one passing from the reference and the sample. The chopper is the two beams are reflected to a chopper which is rotating at a speed of around 10 rotations per second, and this chopper makes the reference and the sample beam to fall on the monochromatic grating alternatively. Monochromatic grating, the grating also rotates, though slowly. This rotation sends individual frequencies to the detector. The detector, at the wavelength where the sample is absorbed, the detector will receive a weak beam, whereas from the sample, while the reference beam will be full beam intensity, and this leads to a pulsating or an alternating current to flow from the detector to the amplifier. On the other hand, at frequencies where the sample does not absorb, both the beams will have equal intensity, and the current flowing from the detector to the amplifier will be direct and not alternating. So these detectors are actually designed to amplify only the alternating current. Examples can be thermocouples, there can be photoelectric detectors. Applications of IR spectroscopy is basically we are working to identify the structure of complex molecules for studying the functional biological molecules, and many police forces across the world that unknowingly they use IR spectroscopy. This is because many breath analyzers they collect evidence to determine level of alcohol in the breath. So IR spectrophotometers, they look specifically for absorption at around 1060, which corresponds to vibration of CO bonds in ethanol.